Hi viewers, a warm welcome to all. In this module, we are discussing magnetism in nanomaterials. That is, this module is exclusively for magnetic nanomaterials. Magnetic nanoparticles MNPs are a category of materials which are comprised of active core coated with a stabilizing shell to which ligands and additional imaging modalities can be anchored. The core is definitely magnetic in nature. Magnetic nanoparticles or MNPs are a class of nanomaterials that can be manipulated using a magnetic field. MNPs are mainly built of pure metals like iron, cobalt, nickel and manganese or their alloys and oxides. MNPs may be mainly paramagnetic, ferromagnetic or super paramagnetic. Characteristics of magnetic nanoparticles. Magnetic nanoparticles have several characteristic features. First of all, magnetism denoted as M. Magnetism represents the extent to which the substance is magnetized under a given magnetic field. The highest value of M, magnetization, attained by the material is known as saturation magnetization MS. Coercivity denoted as HC. It is the strength of the external magnetic field required to make the magnetization of a nanoparticle to zero value. That is, it is the strength of the external field to completely demagnetize a magnetic material. Magnetocrystalline anisotropic constant denoted as K. This constant reflects the energy required to change the direction of magnetization from easy to hard axis. Magnetic hysteresis. It is an important concept associated with the magnetic materials. The term hysteresis is derived from an ancient Greek word means deficiency or lagging behind. Hysteresis is well known in ferromagnetic materials. When an external magnetic field is applied to a ferromagnet, the atomic dipoles align themselves with the external field that we applied. Even when the external field is removed, part of the alignment will be retained in the material. That material has become magnetized. To demagnetize a magnetic material, it would be necessary to apply a magnetic field in opposite direction. The relationship between magnetic field strength H and magnetization is not linear in such type of magnetic materials. If we plot the values of H and M, the result is a sort of S-shaped loop known as the hysteresis loop. The width of the middle section of the loop of the hysteresis loop describes the amount of hysteresis related to coercivity of the material. The picture illustrates hysteresis loop. The main parameters extracted from the hysteresis loop include the saturation magnetization MS, the remanence MR, the coercivity HC. The hysteresis loop is almost S-shaped loop, S-shaped curve. Paramagnetism, ferromagnetism and superparamagnetism can be differentiated by using their magnetic behavior. Considerable difference is observed in the magnetization behavior of such substances under the influence of an external magnetic field. Picture illustrate three types of magnetism together in a single graph: ferromagnetism, paramagnetism and superparamagnetism. Here M represents magnetization, MS stands for saturation magnetization, H represents the applied field strength. The magnetization M against applied magnetic field strength H. Plot of ferromagnetic, paramagnetic and superparamagnetic substance show different behavior. Different shaped curves are obtained for these three types of magnetic materials as shown in the figure. Paramagnetic labels. The incorporation of paramagnetic ions or paramagnetic labels into a nanocrystalline matrix enables the formation of paramagnetic nanocrystals. That is, we can prepare a magnetic nanocrystal, a paramagnetic nanocrystal by introducing paramagnetic metal ions into a nanomatrix. The commonly used paramagnetic labels are trivalent lanthanide ions or transition metal ions. The chart designates some common paramagnetic metal ion labels with their electronic arrangement, unpaired electrons and spin-only magnetic moment. For manganese 2 ion, divalent manganese 2 ion, 3d5 is the configuration. It is having 5 unpaired electrons and the spin-only magnetic moment, which is given by the formula under root n into n plus 2, where n represents number of unpaired electrons, is equal to 5.91 Bohr magneton. In the case of cobalt, the configuration is a 3d7 with 3 unpaired electron. The magnetic moment, the spin-only moment, is 3.87 Bohr magneton. Similarly, for lanthanide ions, the values are given with electronic configuration as well as number of unpaired electrons. For holmium 3, the configuration is 4f10 and unpaired electron is only 4, but the effective magnetic moment is 10.64. Note that the 10.64 value is not spin-only magnetic moment, but it is the effective magnetic moment. The effective magnetic moment is the net magnetic moment obtained from contributions of both spin as well as orbital motion of the electron. Ferromagnetic and superparamagnetic labels. Ferromagnetic and superparamagnetic labels include iron 2, iron 3, magnetite Fe3O4 or megamite gamma Fe2O3. The zero coercivity of superparamagnetic ionoxide SpIO nanoparticles is a favorable feature for biomedical applications. We already observed that in the case of a superparamagnetic material, there will be no S-shaped hysteresis curve, and for the superparamagnetic substance, the coercivity and remanence will be equal to 0. The incorporation of ferromagnetic and superparamagnetic labels onto a nanomaterial enable the formation of magnetic nanomaterials with desired magnetic properties. Superparamagnetic nanoparticles. These are more important type of nanoparticle as far as their applications are concerned. Certain paramagnetic materials has no coercivity and remanence. Such magnetic materials are, I already mentioned, they are said to be superparamagnetic materials. That is, when an external magnetic field is switched off, the internal magnetic dipoles randomize again. No extra energy is needed to demagnetize the material, and hence net magnetic moment is spontaneously recovered. A nanoparticle with such magnetic behavior is superparamagnetic. Size and superparamagnetic behavior. Superparamagnetism is a phenomena which is size dependent. Parameters such as coercivity of the nanoparticle, can be finely tuned by decreasing their size. That is, coercivity is a size dependent property. A further reduction of the size below certain values called superparamagnetic radius, notated as RSP, causes the transition of both the ferro and ferrimagnetic nanoparticle to superparamagnetic. That is, by changing the size or radius, we can convert materials, that is ferro or ferrimagnetic materials, to superparamagnetic. Thus, superparamagnetism is a property strictly associated to nano-structured magnetic materials. Superparamagnetic ionoxide nanoparticles is another area of attention. They are denoted as spions. Ionoxide nanoparticles with zero remanence and coercivity are termed as spions or simply superparamagnetic ions, ionoxide nanoparticles. According to the hydrodynamic size, ionoxide nanoparticles are divided into three categories. They are ultra-small spions, ultra-small superparamagnetic ionoxide U-spio with hydrodynamic size, that is size in aqueous medium, less than 50 nanometer. The second category, superparamagnetic ionoxide, simply spio with hydrodynamic size greater than 50 nanometer. And finally, micron sized ionoxide nanoparticles M-pio. Synthesis of superparamagnetic ionoxide nanoparticles. The spions can be synthesized by several methods. What about the common method? The most common method for the preparation of spion is co-precipitation. Co-precipitation of Fe2 plus and Fe3 plus salt solution with the addition of base under an inert atmosphere yields superparamagnetic ionoxide nanoparticles. The type of salt employed, ratio of Fe2 plus to Fe3 plus, temperature of the reaction, pH and ionic strength all affect the properties of the synthesized spions. The co-precipitation method continues to be most widely used method for biomedical applications since it leads to less hazardous spions. Now, we have to discuss coating of spions. In order to make superparamagnetic ionoxide nanoparticles affordable for biomedical applications and other chemical applications, we have to coat the spions using suitable agents in vivo. This coating has the following advantages. This is to prevent ionoxide core agglomeration. The coating provide chemical handles for conjugation of drug molecules, targeting ligands, etc. Limit the non-specific cell interactions. These points are from biological application point of view. Measurement of magnetic properties. It should be noted that there are several methods for the measurement of magnetic properties. The different methods include GUI balance. It is a device used for measuring magnetic susceptibility of a sample. SQUID, superconducting quantum interference device. It is an advanced instrument, very sensitive magnetometer used to measure extremely subtle magnetic fields. Vibrating sample magnetometer VSM. It is a very popular method used to determine nano level magnetism or nanomagnetism. We can enter into more details of the instrument vibrating sample magnetometer, since it is highly useful for the characterization of magnetic nanomaterials. Vibrating sample magnetometer is used to measure magnetic properties of magnetic materials, especially nanomaterials. The VSM instrument is invented in 1955 by Simon Foner. VSM operates on the basis of Faraday's laws of induction, which states that a change in magnetic field will result in an electric field. This electric field can be measured and can tell us information about the changing magnetic field. Regarding the invention, the inventor Simon Forner belongs to Lincoln Laboratory, Massachusetts Institute of Technology. He published a paper regarding VSM in 1959. His paper is Versatile and Sensitive Vibrating Sample Magnetometer, published in Review of Scientific Instruments. Theory of operation. In VSM, the sample is placed in a constant external magnetic field. This constant magnetic field will magnetize the sample. The stronger the constant field, the larger will be the extent of magnetization. The sample is then subjected to mechanical vibration. The resulting magnetic flux change will cause an electric field in the pickup coil according to Faraday's laws of induction. The current will be proportional to the magnetization of the sample. The induction current is proportional to the magnetization of the sample. The greater the magnetization, the greater the induced current. The induction current is amplified using suitable software. The system can tell us how much a sample is magnetized and how its magnetization depends on the external constant magnetic field. The constant magnetic field is generated by an electromagnet or a superconducting magnet. The main parts of VSM instrument include: number 1, water cooled electromagnetic and power supply, vibration exciter and sample holder, sensor coils, amplifiers, control chassis, lock-in amplifier, meter and computer interface. The VSM detection mechanism is simply illustrated in this figure. That is a sample holder to the end of which the sample is placed, and there are two strong electromagnets are there. The sample holder along with the sample is placed in between these two strong external electromagnet of constant strength. The device is associated with the pickup coil. As a result of the vibration of the sample, some induction current is generated. That induction current is taken up by the pickup coils and amplified and recorded. A typical magnetization measurement of a sample using vibrating sample magnetometer include the following steps. In the first step, the strength of the constant magnetic field is set. Then the sample begins to vibrate. The signal received from the probe is translated into magnetic moment. The strength of the constant magnetic field changes to a new value. The signal from the probe again gets translated into values of magnetization. The constant magnetic field varies over a given range, and a plot of magnetization versus magnetic field strength is generated. Applications of magnetic nanoparticles. MNPs have received tremendous attention in diverse fields because of their unique nanoscale properties and the potential of a wide range of applications. The applications of magnetic nanomaterials, nanoparticles include drug delivery, magnetic hyperthermia, magnetic resonance imaging contrast agent development, tissue engineering and repair, biosensing applications, biochemical separation and bioanalysis. Recently, magnetic nanoparticles are explored in theranostics, which is a combination of two things, therapy and diagnostics. The picture represents applications of magnetic nanoparticles include thermal management, magnetic drug delivery, cell separation catalysis, nucleic acid separation, magnetic resonance imaging contrast agent, for wastewater treatment, biomedical separation, magnetic hyperthermia, magneto-resonance resistant sensors, for data storage and for spintronic applications. Magnetic nanoparticles for hyperthermia. Hyper means high, thermia means temperature. Hyperthermia is a treatment method based on magnetic nanoparticles. It is a promising therapy for the selective apoptosis of tumor cells through controlled heating of the damaged tissue. The procedure involves initially the dispersion of magnetic nanoparticles in the targeted tissue. The application of an external magnetic field induces magnetization of the magnetic nanomaterial within the tumor cell and then apply an alternating field with a high frequency. It causes, the application of the high frequency causes reversal of the magnetization of the magnetic nanoparticle within the cell, and as a result of that, heat is produced. This heat destroys the cancer cells. This is the mechanism. Application of magnetic nanoparticles in magnetic resonance imaging. We all are aware magnetic resonance imaging is a very important imaging modality, imaging method, just like a CT scan, X-ray imaging, like that. MRI is an integral part of modern clinical imaging. MRI offer better medical diagnosis in cancer, cardiovascular, liver and neurodegenerative disorders. It helps to differentiate cancer cells ranging from breast cancer, prostate cancer to brain tumor. MRI is useful to visualize disease associated with the central nervous system CNS, such as Alzheimer's disease, as well as cardiovascular related problems. The basic principle of magnetic resonance imaging, MRI, is based on the common NMR, nuclear magnetic resonance. We all familiar with NMR spectroscopy. MRI is based on NMR together with the relaxation of proton spins in a magnetic field. When the nuclei of protons are exposed to a strong magnetic field, their spins align either parallel or anti-parallel to the external field. As a result, the spin precesses under a particular frequency called Larmor frequency. Larmor frequency, omega 0 is equal to gamma into B0. B0 is the strength of the external magnetic field. In the presence of the external magnetic field, spin of the nucleus happens, and such motion is known as the precessional motion. When resonance frequency in radio frequency range is introduced, the protons absorb energy and are excited to the anti-parallel state. After disappearing of the RF pulse, the excited nuclei relax back to their initial low energy state or ground state. There are two types of relaxation procedures. They are nothing but T1 and T2 relaxation. The first is T1 or longitudinal relaxation, which involves decreased net magnetization recovering to the initial state. The second one, which is known as T2 relaxation or transverse relaxation, involves induced magnetization of the perpendicular plane MXY disappearing by the dephasing of the spins. T1 and T2 relaxation graphically are represented here. A more thorough discussion is far beyond the scope of the present lecture. Now, contrast agents in MRI. In order to enhance the sensitivity and the diagnostic capabilities of magnetic resonance imaging, a supplementary exogenous substance known as contrast agent, denoted as CA, is introduced prior to recording of MRI image. Contrast agents can selectively enhance the water proton relaxation time at the tissues itself, and hence the precise differentiation of similar closer type of tissues can be achieved. The contrast agents in MRI can be broadly divided into two categories depending on whether they provide brightening or darkening effect on the final MRI image. Contrast agents that decrease longitudinal relaxation time of water protons more than their transverse relaxation time leads to a brightening effect. Those contrast agents are denoted as T1 contrast agents, but some other contrast agents decrease transverse relaxation time of water protons more than their longitudinal relaxation time. This leads to darkening effect in the MR image, and such contrast agents are denoted as T2 contrast agents. T1 contrast agents and T2 contrast agents are otherwise known as positive and negative contrast agents respectively. Application of magnetic nanoparticles as contrast agent in MRI. MNBs are extensively used as MRI contrast agents. Some examples are gadolinium based T1 contrast agents. Several gadolinium 3 complexes are used for this purpose. Ionoxide based T2 contrast agents. Superparamagnetic ionoxide nanoparticles pions are used as T2 contrast agents in MRI. Dysprosium and holmium based contrast agents. Recently, contrast agents based on paramagnetic nanomaterials contain dysprosium or holmium, also used as T2 contrast agents. Thus, in this module, we discussed magnetic properties of nanomaterials, different type of magnetism, applications of magnetic nanomaterials with a special emphasis to magnetic resonance imaging. That all about this module. Thank you.